I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks, and I'm joined, as always, by my trusty co-host, Andrew Falkowski, and our audio guru, Jared Duffy. Guys, how's it been?
It's going. It's finally getting warm, but, school and projects are just destroying me.
Yeah, I loved the lack of spring break this year. That was a really good academic
That was a really nice touch.
There's nothing I love more. And it's to the point now, because I'm in some classes, and I have like 6 tests in these classes. It's like, how is this a midterm if I'm taking one every 2 weeks? That's not middle of the term.
Guys, I did full-on Galaxy Brain this year. I did a half-semester class that ended like weeks ago, and I'm just coasting now. I'm just writing grants. It's like I'm not even a teacher. This is amazing.
Yeah, I TA'd that class, and for some whatever reason, I'm still answering students' questions.
We made the mistake of saying they could turn in their final project till the end of the semester, which to them was, okay, I'm going to do nothing about this.
That makes it a final project.
Weeks.
Yeah, no. And then I've got 3 jobs total, too, so I'm busy. I got 2 podcasts and an internship. I keep busy.
Busy. Well, we are so excited for today's episode, but first I have to set the scene for it. So go way back in time with me. Go in the Wayback Machine to young Taylor sitting on his parents' bed watching night TV. My favorite show was on. Here's a clip from it.
Tea, Earl Grey, hot.
Tea, Earl Grey, hot.
Earl Grey.
Tea, Earl Grey, hot.
So if you recognize it, if you ever watch the show, that phrase will be familiar to you because that is Captain Jean-Luc Picard. And he is talking to his computer, which in and of itself was, prescient. It was looking forward in time for sure. But he was talking to the replicator. And the replicator, I remember my young mind seeing this thing about the size of a microwave, and you could just tell it what you wanted. And out came what you wanted. It'd make you a food, it'd make you a whatever. And now we live in that future because we have devices. It's not quite that quick, and we don't talk to them yet. We probably could. But we can have these little boxes spit out at least shapes for what we're looking for. And that's going to be the content of today's episode. The long-awaited 3D printer episode. That's right, folks. We're finally doing it.
Yeah, we were kind of nervous to even do it. It's such a important and very hot topic at the moment that we wanted to make sure we did it justice. So in preparation for this, we did a lot of reading. I read a textbook. It's a pretty good one. It's Additive Manufacturing Technologies from Gibson, published by Springer. It's pretty good.
No one has ever said that sentence before in their entire life. You read a textbook for fun?
Andrew's not your average guy.
Yeah.
I wouldn't say it was for fun, but I did it for the podcast. I took one for you, so you don't have to read it. It's pretty good. If you're really interested in the topic, I'd give it a read, but the figures are really low quality. You can tell that whoever's editing it had a low resolution monitor, and they're like, yeah, those look good. And then they just
Stripe Press, come fix this. So, this idea of 3D printing is so cool. It's captivated not just people in the 80s making Star Trek, right? It's been around for a long time. All the way back to 1945, we get this cool story of the first mention of what sounds like a 3D printer from Murray Leinster. He writes this short story called Things Pass By, and there's this sentence inside it that says this: but this constructor is both efficient and flexible. I feed magnetronic plastics, the stuff they make houses and ships of nowadays. I love that. Into this moving arm, it makes drawings in the air. Following the drawings, it scans with photocells, but plastics come out at the end. The drawing arm and then hardens as they come out, following the drawings only. How amazing is that? That is a 3D printer it's describing. So this has been, imagined for, 70 years, whatever that's been. But it wasn't really until the 70s and 80s that this kind of started to take place. And as we were reading the history on this to get ready for this episode, it was heartbreaking because you read these false starts by these companies that got so close to stumbling onto it earlier, like April 1980. Hideo Kodama at Nagoya Municipal Industrial Research Institute. He basically invents it. He invents what we would now call SLA, right? Which we'll talk about a little bit later. It's a type of 3D printer. He calls it the XYZ plotter, and they do a provisional patent on it and publish some articles. But then get this, it says, however, there was no reaction to his series of publications. The device was not highly evaluated in the laboratory, and his boss did not show any interest. And his budget was only $545 a year, which was nothing. And acquiring the patent rights to this XYZ plotter was just deemed it was abandoned because it was too expensive.
You can't even get a good 3D printer for
I know!
$500.
And they could have invented. So, and then it gets worse. Like 2-3 years later, another one in France this time, July 1984, a series of authors put together a patent for their stereolithography process. And it says the application of the French inventors was abandoned by their company, the French General Electric Company, because they claimed it had, quote, lack of business perspective. Oh, it's just brutal. At this time, the very first 3D printers that were showing up were very expensive. We're talking like $300K in 1980s dollars, which is over $500,000, $650K or about right now. And that's pretty wild considering what you can buy now. Today, you can buy one for $300. That's an amazing machine. So what's happened between now and then? What is going on here, Andrew?
Understanding the transition in how the technology was appreciated and what sort of technologies it's built off of, and those developments kind of put these false starts into context. So originally, this technology was referred to as rapid prototyping, and just simply the name kind of constrained what people thought it was possible. What was possible with this technology, right? You're just thinking of prototypes. Oh, this is just a way of making 3D models, right? Like there's no real application that's happening here. It's only really in the recent decades that we've seen a shift to the term additive manufacturing, and very recently, as it's become very popular, we see the rise of just calling it 3D printing.
Well, I think also that name is definitely something that's kind of interesting because that is really how, at least me in my academic life, I've treated it as a rapid prototype. And every time I use 3D printing, it's usually to design a project, and I feel oftentimes that I go through like 3 or 4 prints of one item before you really nail it down perfectly.
You know what's cool? There's been a really cool transition from treating this as a prototyping only thing to treating it as all of a sudden this thing can spit out a product that you could sell. In fact, I was reading this article. One of the articles I read, this was a big review on additive manufacturing, and they had this really interesting statistic that said this company, Wohlers and Associates, found that by this year, 2020, 50% of all 3D printing is actually going to be the final product and not prototyping anymore. So there's been a transition. It's no longer just to like try something out in a cheap way. Mm-hmm. We are getting so good at it that now we're selling components which are 3D printed.
Well, it's also because the filament's getting a lot more high quality than it was obviously in the past. Like I remember the first thing I ever 3D printed was like 6 or 7 years ago. I made a really kind of messy flashlight that didn't do a great job. It was like the circuit board was made using a copper like board with just Sharpie drawn on it, and then you dipped the Sharpie in some sort of chemical that dissolved it and made really crude like circuit lines. It was definitely something.
So we will have a future episode all about the incredible things, the applications of 3D printing. But before we do that, we would be doing you a disservice to not dive into the science and explain the basics of how it's actually working. So before we do that, maybe we talk about where it's coming from. But when you print something, you have to feed it a file. What is that, and how do we get it, Andrew?
Really, before we even talk about the STL file, I think if you think about 3D printing and what goes into it, all of the different technologies, the components here are somewhat simple. It's really just the bringing of them together, but they all required separate development, right? We needed to have efficient, consistent extruding technology where we could melt plastic. We needed to have servos and actuators where we could move.
And that's been around for a while. Like that stuff's not rocket science.
Right, yeah. Reaching a level of precision as well as being able to be manufactured somewhat cheaply, laser technology and making that more cost effective and consistent as well, and targeting specific wavelengths as well.
But the file itself, you're saying, the way that we store this information and to render these sort of drawings, that really wasn't until later on that we got that capability.
Right, yeah. So all the patents and a lot of the emerging first systems come about in the 80s, which is when we started to get computers that were powerful enough to even render three-dimensional drawings or descriptions of objects. But even then, to take it and just do it, a perfect representation of this 3D object becomes computationally difficult. And when your extruder can only operate in, X, Y, and Z directions, and it moves typically along just lines, and that's what it's depositing essentially, it becomes more effective to simplify this geometrically further. And that's where this STL file that's really popular comes about, which stands for standard triangle language.
Yeah.
Essentially breaking a three-dimensional object into triangles where it's easier to process. And these are sort of the developments and the technologies that represent the core of this technology.
Okay, so we're going to dive into each one of the different types of the 3D printing technologies or additive manufacturing technologies, and there's 4. Let me just give a very brief summary. You've got the one which you're probably familiar with at your local library, at your nephew's house. You've seen it. This is the fused deposition modeling. This is one where there's a little tiny print head. It's like a hot glue gun on, steroids. It basically, a filament gets fed in from the background, it melts it in real time, and it deposits it in real time, right? But that's only one type, actually, and it's actually one of the later ones that was developed. The ones that were patented earlier than that. So you've got your SLA, that's stereolithographic apparatus. We had to Google that, right? But this is the one where you have a vat of polymer liquid, right? And then you introduce a light of a specific wavelength in a certain way that where the light hits that fluid, it now polymerizes it, right? So if you've listened to our previous episodes on polymerization, you know that light activation is a pretty common way that you can achieve polymerization. And this just does it in a really controlled way where it shines the light with a known intensity in a certain spot until you get the pattern that you're looking for. And then they'll raise the bed up or lower it down depending on the geometry of the system, and they'll shine the light on the next section that's apparent. So it's another layer by layer technique, but it can achieve pretty high resolution. Then you've got your powder bed methods. How do the powder bed methods work, Andrew?
Right, this functions similarly to the vat polymerization method, except instead of being a liquid polymer solution, you have fine particles. And then using a laser, we essentially sinter them together to form, layer by layer, to form a solid part. So just like with the vat polymerization, once we create one cross-section of our part, we recoat the powder, so we have a new layer of powder on top, and then this is then hit with another laser to sinter this next cross-section.
Yep. And an alternative version of that would be binder jet printing, where basically you take that powder bed, and this time you just, imagine just drizzling super glue over it. Where it gets drizzled, it's now sort of stuck together. It's much more high-tech than that, but that's the idea. And then you've got inkjet methods. Inkjet methods are essentially kind of like the 3D printing that you're familiar with now, except that imagine if you had another particle embedded inside of the stream that gets printed, right? Maybe you've got a solvent and you've got sand or something inside of it. Well, as the solvent gets removed, you're left with the sand left over. So think of it like it's a composite that's getting sort of extruded out from the tip.
All right, so we're going to break down the 3 most popular of these and the ones that I think are most relevant. Starting with extrusion systems. These are the ones that I think most people are pretty familiar with. We start with some sort of solid material that's fed into an extruder where this solid material is melted into a liquid molten form, and then through applied pressure is extruded from this, and it slowly deposits it in lines. Right? If you've Googled 3D printers or if you've been around on Instagram, you'll see this is the most popular one. It's a lot cheaper than other processes, and it's more easy to commercialize. So this is the most common commercially available type that's out there.
One downside of this approach is that you actually have pretty few knobs that you can control, right? There's like the resolution of the head. You can change the diameter of the aperture that it's coming out. There's things like temperature and print speed, then obviously like the layup of the actual printing. But it's kind of limited because ultimately you're just melting that material, and that as it melts, it has its own rheological properties and it's going to settle out. But you have limited processing parameters to sort of tune there.
Yeah, that said, there's still quite a bit of things that can be adjusted. And I think from a commercial standpoint, right, if you buy a 3D printer, there's probably not a lot of knobs you're going to be able to adjust. But in research setting, there's quite a bit that they'll do and experiment with, right? So fundamentally, it's about liquefying some amount of material. And ideally, right, having this feed system where you have to melt it and then, continuously feed material into it, it's a potential bottleneck in how much you can extrude at a time, how much is available. But let's just say we created a larger chamber where we're going to melt all this plastic. You then have issues with heat transport.
Yeah.
And you might have things where along the edges where your heating coils are, it will be nice and melted, but towards the center, there might be still solidified chunks, which is undesirable. At the same time, if you go too hot a temperature, then you might actually burn some of the material to the inside of this extruder, which could then build up. And
Yeah, when the extruder fails on ours, we just buy a new one. I don't even bother trying to fix it. And they're like $200, and we just buy a new one. In comes a new one. I don't want to mess with it.
See, there's too much funding in academia. You just buy new ones.
Yeah, I had to clean one of those once. It was me who broke it, but I had to open that thing up, and it was one of those things like, okay, take pictures of every step so I can reassemble this thing. And I got it, but it was kind of a pain. At the same time, you also have the diameter of your extrusion nozzle, so how fast you can how much material can actually come out at a time. And there's kind of a trade-off, right? If you have a smaller diameter nozzle, you can get a higher resolution, but that means the amount of material you can put out at a time is smaller, so prints are going to take a lot longer.
Yeah.
And when we think about the economics of 3D printing, right, it's not just meant to be a novel thing. If we want to think about this in a commercial application or start printing parts to be used in actuality, really the speed of production is an important factor. So if the only way to compete with other processes is to take a really long time with this really high resolution nozzle, it might come out to not be worth it because time is money.
Yeah. Another one of the big drawbacks to fused deposition modeling is that the parts you get out have two issues with mechanics. First off, they're weak. And anybody who's welded before, this kind of makes sense. Where's the weakest spot on anything that you put together? It's the weld joint. And these are made basically of welds, right? You're melting material and having it stick to something. So it's one giant, miles and miles of welds all stuck together. And then the other problem is because you make this in a layer by layer fashion with this welding technology, you get anisotropic properties. If you're not familiar with anisotropy is when you measure a property in one direction. Let's say like if you have like you printed a gear, if you test its strength in one direction as opposed to orthogonal, in plane, and you get different values, you have an anisotropic properties there. And that's what you typically get with 3D printing, and that can be not desirable.
Yeah, a lot of this has to do with the bonding and the physical forces that are acting on the extruded material. Now, ideally, you want the previous layer to still be somewhat melted when you're applying the next layer so that you get a bond between them, right? Because if it fully hardens, then you're essentially just layering materials on top of each other, and you're not actually getting a solid bond between them. But if you melt the previous layer too much, then it's too much of a liquid state. It's not going to have any sort of, it's not going to have enough structural integrity to support the subsequent layers on top of it. So you have a challenge here, right? And then you also have to think about cooling. You're going to get shrinkage from these. And of course, because it's a liquid and it's deposited in such a way, you get non-linear shrinkage. So it becomes, very difficult to predict.
We had some components we were printing, and ultimately it was failing. It was like the print head was crashing into our component. And what we ultimately realized is it was due to thermal fluctuations. Our part wasn't being held at the same exact temperature. And as it expands and contracts, especially if you're printing at a small resolution scale, it was actually crashing. It wasn't going to the spot where it thought it was going to be because the part was, it's moving a little bit as temperature gradient. We ended up putting a big box around it and putting a temperature controller on it, and dramatic overnight improvement, like much bigger improvement there.
Right. You want to reduce the thermal differential between the extruder and the actual environment.
Yep.
And there's also some really good, fun external forces. I don't know if you guys have seen this photo floating around. I think I saw it on Instagram a few times. It's this guy, he goes, ruined a 36-hour print because of a glue stick. He had a glue stick rolling underneath the bed, and so as the bed's going down to print further and further up, it hit the glue stick, couldn't go down all the way, and so he just had, the last inch just wasn't finished, and the whole thing was ruined. So funny.
Brutal. Anybody who's printed can feel your pain.
The other thing you have to think about is you're moving this crosshead around with the extruder on it, and because as you change directions, right, there's acceleration, deceleration, and stopping, you're typically not actually modifying the rate of extrusion. And so when you're decelerating, more material is going to come out in those areas. Same with if you stop and start. So typically, this goes into the software itself and is a little more complicated, but it will generally pick a start and stop place for each layer. If you keep stopping and starting in the same place, you'll have kind of a seam that gets built up. And so to try to avoid this, sometimes they'll have random start and stop places, but it's kind of debatable whether you want the seam, because then if you have it, then you can easily apply some post-processing to that area.
Geez, hearing all this, it's probably evident now to our listeners why this hasn't become as mainstream. There's a lot of bugs to overcome here. It's going to be weak. There's going to be flaws. You're going to have imperfections. And yet it's gotten a lot better. The technology has improved a lot. We can print things pretty small. Say, for example, with this fused deposition method, the resolution that you can achieve is, according to this table I found, it's saying that you can print down to 50 microns to 200 microns is the resolutions that are typically available right now, which is pretty phenomenal. It's like a human hair, essentially. We can do better, though, with other techniques, which we'll get to.
Yeah, another one of the challenges of 3D printing is building parts with overhangs, right? The beauty of 3D printing is that we can make complex parts in a single run. We don't have to break it up into a bunch of things and do all these different manufacturing processes and then join them together. We can ideally make it in one go. But because you're applying layer by layer, what happens when you start to make a layer that is wider than the previous one, right?
Yeah, or what if you want to go somewhere where there's no layer underneath it, right? You want to start something in some spot where there was nothing there before.
Gravity still exists for 3D printers, and so what they do is they actually build scaffolding and supports to basically create temporary structures that it can build on top of. And these work pretty well, But the challenge then is, right, now your build time increases if you have to make a bunch of supports, because now it's not only the part build time, but also now the scaffold build time. And those supports are bonded somewhat to the part itself.
You got to break them off afterwards, and then you've got, imperfections.
You have small little knobs. Some ideas have been, we've shown that if you take longer to make a part and allow the previous layer to cool, you don't get as strong adhesion. So it's possible if you timed things correctly, you might be able to snap it off. But this becomes challenging.
Anybody who's actually used these and actually trying to like sand it or clean it off, it's actually tricky to get it, depending on what material you're printing with. But in my practice, it's been hard to get it nice and smooth afterwards. It's not trivial.
Yeah, there's definitely there's an art to it. Like a little bit of wet sanding, a little bit of dry sanding. It does take some time.
It's a little tricky.
The more expensive 3D printers will actually have 2 extruder nozzles with different materials, one of them for the scaffold and one for the main part. So the scaffold will be made out of either a softer, weaker material, or it'll be made out of material that can dissolve. So they'll take the part and they'll just put it into some sort of solvent, and it'll completely dissolve the supports away. So if you really are trying to go for quality, something that can be used and reducing the time of processing, this ends up being the better route for that.
So the materials that you can use, basically it just has to be a thermoplastic, right? It has to be something that will melt. It's going to be rigid while it's a filament. It needs to be meltable so it will flow, and then it needs to be able to cool off. Ideally, this happens at a temperature that's not too hot, so your print head doesn't have to get too hot for this to happen. Obviously, the flowability of this is going to come into it. And because of this, there have been a few materials that the industry is sort of focused around. So if you've printed, you know that ABS is a winner, and then PLA are both winners.
Yeah, and it's not just ABS, right? They may have started with stock ABS, but they've added a lot of different additives to specifically improve the final properties and the flowability of these polymers as well. And typically what they go for are amorphous polymers, so they don't have any sort of repeating structure here. And the reason they go for that is because amorphous polymers melt over a wide range of temperatures, and they also don't really melt in the same way that we think of it. They kind of just become increasingly less viscous. Yeah. And so this is desirable for a situation where you want to deposit something and have it solidify without shifting its shape too much. Imagine trying to deposit something like as viscous as water. It'd be very difficult. There's a lot we could talk about with this topic. It kind of goes on and on. There's all sorts of little specialties, but just to move on to the next really big area within this field, vat polymerization. This was one of the first types that really came about because from a processing standpoint, it's a little simpler. But back then it was called stereolithography. And as Taylor already went over, just to kind of reiterate, essentially we have a vat of liquid polymer that cures via photopolymerization, so reaction with some sort of light. And rather than extruding the material is already there. So we take a build platform and we use a laser to trace the outline of the cross-section of the layer that we're building. And when the laser interacts with the polymer, it initiates a reaction in that local specific area where the light hit.
Because you're doing this with a laser, we're talking really small scale. Of all the different techniques we're going to talk about today, I think SLA has the highest resolution. It can go all the way down to 10 microns, which is bananas, right? And you've seen it. If you've seen really nice 3D printed parts, it probably wasn't a fused deposition technique. It was probably SLA. You can really tell when you pick them up.
Yeah, we have one in my lab that I've used quite a bit, and the parts look really great. And there's a lot of different types of resins that you can use with this as well, which we'll get into. It's interesting because they have, there's 2 kind of methods here, right? We have a vector scan approach where, let's just imagine, your typical laser with a fixed point, and you scan it, along the XY area, and you trace your outline, kind of just like the extruder, but this time it's just the area of the laser. But an interesting thing I came across was a mask projection approach. So if we already just have to use UV light, for instance, to cure this, why even waste time moving a laser around? What if you could just illuminate the entire cross-section at once?
This is the idea behind photolithography, right? And then you can also shrink it, right? You can pass it through a lens so you can get miniaturization. So your mask doesn't have to be the exact same size as what gets shown on the object. You can pass it through a lens. So really, really cool things are possible.
And the way they accomplish this is with these digital micromirror devices. And I think you should look these up because it's really cool. Essentially, they just have a sheet of tiny mirrors that are on little motors that can manipulate them. So essentially, they can shine the UV light and then use these mirrors to form the cross-section of the layer that's going to be built. And so they can essentially just polymerize the exact layer they're looking for right there by just orienting all these tiny little mirrors to make sure they hit the right spots. These are naturally going to be a lot more expensive. And if you're polymerizing an entire layer at once, there's some other trade-offs you have to consider, but I think it's really cool that there's so much customizability. And when we're talking about time it takes to complete the reaction, this could be a potentially interesting option of speeding up the time it takes to make each layer. The first patents for vat polymerization materials came about in 1989, 1990 for acrylate resins. And these had a high reactivity, so very fast polymerization, pretty predictable, but they produce relatively weak parts due to shrinkage and curling. Acrylate resins work via free radical polymerization. So essentially UV light cleaves a carbon-carbon bond to produce these highly reactive free radicals. These are just single electrons that really want to bond to something. And what happens is you create essentially an initiator here that is this free radical, or well, the cleaved initiating chemical, now with free radicals attached, and via kind of a step approach, it will slowly build out a long chain of all the monomers, right? And once these chains that are forming get long enough, they can kind of get a lot closer to one another, and then we start to get this cross-linking phenomenon, so essentially bridges between the polymer chains that makes it nice and hard.
There's this problem where you want it to cross-link, but that gives it its strength, but it's also causing these other problems because that causes it to shrink. So you have this trade-off between those two things.
Right. So when the UV light hits it, actually it only really cures to about 46% completion before the next layer of polymer or of monomer solution is put on top. So really you have a only partially cured polymer. And so the problem becomes the layers are so thin of this monomer solution that the laser will penetrate to that previous layer that was already partially cured.
So they have to design for that because they know it's going to keep on polymerizing past the layer.
Right. So, oxygen is found to inhibit the reaction. So I think when you have the initial curing with the UV light, it only cures so much because oxygen inhibits and kind of terminates the reaction. But now once we put another polymer layer or another monomer solution layer on top of that, the laser goes through, the reaction starts again. So it continues to cross-link. And so that part that's lower is going to shrink and condense a lot more. And so this kind of brings up a lot of the issues with residual stress and shrinkage. And so this prompted people to expand on this and search for alternatives. And that's where epoxide resins come in. So these first really appeared in 1988, mainly from Japan. And these were able to produce more accurate, harder, and stronger parts.
These are thermosets now, right?
No.
These are still thermoplastics.
Oh, no. They are photo-initiated. But this time it's a cationic polymerization. So in this case, we're reacting with, it's typically a Lewis acid serving as a catalyst. And with the addition of light, we basically create a free cation in the solution, which then will bond with a double bond in carbon in order to essentially create a charged carbon species that can then bond with other monomer units. And this really functions off the epoxide ring opening mechanism. So an epoxide is kind of like a triangle, if you look it up. And so through this reaction, essentially it opens up this ring to form a longer chain. And this doesn't result in shrinkage because the number of bonds doesn't change. You're not forming anything new. It's just an opening process. And so if acrylate shrinkage will be anywhere between 5 to 20%, epoxide shrinkage is like 1 to 2%.
That's a huge improvement.
And the other thing is it's not inhibited by oxygen in the atmosphere, so you can have lower photoinitiator concentrations, so you don't have to have as much of the initiator in there because it's not going to be inhibited. At the same time, these reactions are a lot slower than acrylates. They're not as photosensitive and they don't happen as fast. At the same time, the materials that are produced are more brittle, and they're also really sensitive to moisture, which can be an issue. So in practice, they actually usually mix a little bit of both of these to make up for the failings of each. So this doesn't form a copolymer, as you might expect. It actually forms a blend, right? Yeah, it's two interpenetrating networks of the two. And even though they're separate, they're not polymerizing together, they do affect each other. So the presence of the acrylate will increase the speed at which the reaction occurs. It reduces the energy requirement and lowers the humidity sensitivity of the epoxy polymer. And the epoxide serves as a plasticizer that will increase the mobility of acrylate chains and makes it so it's not as sensitive to oxygen inhibiting the reaction. So typically, if you're formulating a resin, more acrylate means faster cure but more shrinkage. More epoxy means a slower cure but less shrinkage.
Yeah, so if you're just prototyping, maybe you can put up with that slower cure time because you just want a good final product. You're only making a few. But in industry, if you're going to be producing these things, you might want to actually go for the faster cure. It might be more economical, which leads to us basically settling for different scan patterns. If you're going to have something that you know is going to shrink more because you have less epoxy, it's going to change the scan pattern you're going to use. So we found that there's a couple different ones. The two ones that you hear talked about are weave and star weave. So weave is going to be the first parallel. The first layer is going to be parallel to the x-axis, then the second parallel to the y-axis. Whereas in a star weave, you're offsetting these scans, leaving space for one another, and this is going to accommodate for more shrinkage. So if you're moving away from epoxy, then you're going to want the star weave, which is going to allow you to accommodate for that shrinkage that might happen.
Yeah, these are a little more complicated than we're making them. Really, the star weave improves on a lot of the failings of just the base weave. And it's funny, you think we're just saying like weave like the word, but these are actually acronyms for things, which is kind of funny. But definitely look those up if you're interested. Some of the main advantages if we're just kind of bringing this section to a close is one, you get really great part accuracy and great surface finish. If you're thinking about something that you'd want to be just direct manufacturing, you 3D print it and you give it to the customer with as minimal post-processing as possible, this would probably be the route you'd want to go. It's also highly configurable. You can accommodate a lot of different material systems. It's really just as simple as swapping out the resin container that you're using. There's some cleaning, but it has a lot of different types of materials that can be used, and there's different laser types and such. And also, with the ability to use a mask approach, you can greatly increase the speed of production. Some of the disadvantages, though, is that you're really limited to photocurable polymers, and really that means like epoxies and acrylates. These, even though they look really nice, they're not going to be able to compete with the strengths of injection molding approaches. And these materials are also known to age quite poorly over time, so they don't have the longevity of other approaches as well.
So we are 2 down. We've talked about fused deposition. We've talked about stereolithography. Let's dive into powderbed fusion, which is really has multiple topics in and of itself. So this came out of the University of Texas, Austin, and they did what's called selective laser sintering. We still talk about that term. That's still one that's around today. The idea being, again, you start with a sandbox, right, of metal powders, right? You try and pack those together. They don't have to be metal. It can be other materials.
It started with plastics.
Oh, they start with plastic?
Yeah.
Oh,
the first iterations were with plastics.
Very, very cool. Which makes sense. It's easier to melt, lower, so you could use a smaller laser, less energy. But in any case, you need to you want to pack that dense together, right? Because you're going to rely on it to now sinter or bind together. And if you don't get it dense now, you're going to have to get it dense later or deal with the porosity left over. One way, pick your poison. But you try and get this dense together, and then you shine a laser on certain parts, and that is either going to completely melt it or it's going to soften it, and that's going to cause those particles to now bond with one another by the same mechanisms we've talked about in previous episodes. This is sintering, basically. This is diffusion, and it's going to cause them to come together and stick a little bit. When you've got your layer bonded in all the spots where you want it to bond, you now bring out the roller and you bring in a new layer of a very carefully controlled thickness of metal powder or polymer powder or whatever it is, and you repeat this process over again.
And there's a number of considerations here.
Yeah.
It gets actually pretty complicated. Initially, they did start out with plastics, mainly due to limitations in laser power. It wasn't really until we have very recent high-powered lasers that were at least affordable enough to be put into one of these machines.
Too. Our lasers now are really fast.
Yeah, and fast enough. And so because they don't want to have the laser actually do all of the printing, they actually typically have a number of radiative and convective heat processes going within the chamber to keep the powder bed as close to its melting point as possible without...
The laser just bumps it over the edge.
Mm-hmm. Yep, exactly.
That's cool.
The other advantage of this is with the extrusion and vat polymerization processes, we talked about how you need to have supports or some sort of scaffolding. Because the powder is dense enough and generally thick enough, the powder itself can serve as a support. And
it's
so
like digging for dinosaur bones. Like your part's in there embedded with all the sand around it, basically.
Yeah. So you don't have to use supports as often with this method, which can mean that the surfaces look a little nicer. There's less post-processing, but this doesn't end up always being the case. When we're thinking about the materials that can be used for these, pretty much any material that can be melted and will solidify in cooling can be used. So let's start with polymers. Thermoplastic polymers are kind of the way to go here. But in this case, unlike in the extrusion system, crystallinity matters.
Yeah, with the extrusion, you wanted it to basically happen over a long range. But here you want, if you can help it, a very close transition from solid to liquid or solid to softened material.
Yeah, exactly, right. You want it to be extremely predictable so that and really controllable, so you know that your laser will in fact melt it and that it won't prematurely melt from the radiative heats as well. So we really want some sort of polymer with a well-defined crystallinity, And typically what they actually use is polyamide or nylon for these, because it's quite crystalline. It has very predictable melting temperatures and behaviors. But the problem with this is that these crystalline polymers exhibit higher amounts of shrinkage, and they're susceptible to curling and distortion. And so really temperature control becomes pretty important for these. These parts actually do approach the mechanical properties of injection molded plastics, which makes it possible for these to compete with those from a manufacturing standpoint.
And it's cool when you actually see these being done. The lasers are moving so fast. You think it's happening everywhere, but it's just incredibly rapid. So they can actually get realistically pretty high speeds with these things when they manufacture them as well.
Yeah, for sure. And sometimes it's not necessarily, this was kind of an interesting way to think about it. Rather than thinking about, we're making the plastic part, in casting applications, polystyrene will be used as kind of a sacrificial mold where it then gets dissolved and replaced with metal. And so they can print in polystyrene. They're not worried about porosity or all these other issues, right? But that way they can essentially print a very high quality sacrificial polymer that'll then be replaced by a metal in a casting situation. So it can kind of help facilitate the manufacturing of other things as well.
So polymers are rad. It's awesome that we have things like nylon that work well for this. But really, when you see powder bed fusion, it's probably a metal that you saw. Metal 3D printing, now we're looking like something I saw in my replicator in Star Trek. This is amazing, right? And this is primarily what it's known for. It doesn't work for all metals, though, actually. It's pretty persnickety, right? Because metals, you have to think about what's going on here. What if you had a material like aluminum, which has a pretty high thermal conductivity, right? And it's prone to forming that oxide layer. That's going to influence how it's going to bond to the neighbors nearby it. Actually getting it to work, finding a 3D printable aluminum alloy was a pretty major undertaking that was just only accomplished not that long ago. It was 5 years ago or something in a paper. This is UCSB and HRL figured out how to do that. There are other materials that are a little bit easier to work with, right? 1996, Rapid Steel was doing this with 1080 carbon steel, beloved steel. But it wasn't just the steel itself, right? Isn't it the case, Andrew, they actually had a binder mixed with it?
Yeah, like I mentioned, the lasers just weren't powerful enough to be straight up, melting and causing the fusing of these metal powders on their own. So typically what they would do is they would actually have a binder system that would bind all these metal parts together. Then they would go and it would undergo a debindering process where they would melt all the plastic out of it. They would then essentially sinter these particles together. But because you got rid of all of the polymer, there's all these voids. So they would infiltrate this with another metal, something like copper, and then they would get the final part.
Bonkers.
But copper actually has a higher, it melts at a higher temperature than the sintering temperature, which is, so it sinters at about 1,000 degrees Celsius, but copper you need to get it to about 1100 C. And so you have this problem. So later iterations shifted to bronze. But it becomes this really complicated process of basically creating a bunch of voids and then introducing a later material.
So where are we at today? Because I know that there are now currently lots of metal alloys available. In fact, I was doing some digging on this, and I found that the number of alloys that are out there has grown pretty dramatically. Yeah, in 2014, when you look at the metal additive manufacturing market, in 2014, there were 49 companies selling this, and only 2 years later, that number had doubled. Right? And 50% of the materials being sold were metals. So we're getting better at this. We're figuring out what's really driving that change. Are we just improving our lasers? Are we finding alloys that are lower melting? What's really driving that?
Yeah, a lot of it is improvement in the alloys themselves, as well as the technologies available. With the advent of electron beam melting, which we'll get to in a little bit, they were able to start fusing together engineering grade metals like titanium, nickel-based superalloys, cobalt, chromium, molybdenum, creating engineering grade materials and products via this method. And even now, new alloys are continuously being designed and researched to make them better for this specific method.
Pretty cool.
But recently, it's not just metals. They can now actually do some ceramic materials as well, though this is a little bit limited. So there are commercially available options for alumina and titanium oxide. And so sometimes there's also instances where they'll create a ceramic material by a reaction with the atmosphere. So if they have aluminum and they're sintering that together, it reacts with a nitrogen atmosphere to form aluminum nitride. And so that's another way. But typically what they do is they will actually just use some sort of binder and then they will sinter it later. But the advantage of the process, right, you're like, oh, okay, you have to go sinter it. What's the point?
Yeah, but Netshaping Ceramics is a big deal. And that's the whole reason why we do things like fugitive wax casting. That also gives you a green thing, which is you have to sinter that thing together as well. But now you can make really complicated shapes that would have been a nightmare to cast. Like that was my whole undergrad. We did a ton of casting, and it was really hard.
Yeah, that's what I'm doing now, and there's so many issues with it. If you could get over that and just get to the sintering, it would be a huge advantage.
It sticks to the wall. You have to get it to release. You get the water. If you're casting it from a slurry, you have to get that water out. It's a pain, man. If you could just basically get it in the right shape and it's held together by glue, you're going to burn that glue off anyways, right? The polymer binder. This is a very powerful technique.
And they've used it to create some really interesting composite materials as well. So, right, think about you have your powder. You can kind of control the density by thinking about how the polymer binder is set up and then infiltrate this with a metal. But a really interesting application I saw, or I guess approach to this, was they took silicon carbide and then they will, they'll infiltrate it with a polymer that leaves behind a residual carbon, and then they melt molten silicon and have that infiltrate it, and it reacts to form more.
With CVD, they did the exact same thing, but it wasn't 3D printed, it was cast. So this is just a better version of that. Yeah, polymer-derived ceramics. So ceramics that use the carbon or the nitrogen or whatever from the polymer. Let's say you burn this thing off not in an oxygen atmosphere, in a reducing atmosphere, or in a vacuum. Now that could become part of your ceramic if it was the chemistry was right. So pretty powerful technique. So we've talked about the different materials, plastics, ceramics, metals. All these are now, you can use this technique for them. But we haven't actually described how you're actually going to bring these particles together to actually fuse them. You've shined a light on them, whether it's laser, maybe you drizzled some glue on them, but how do you actually get these things to bond together? There's a couple different ways possible. You've got your old-fashioned solid-state sintering, right? So let's say you loosely got them sticking together, but it's what we would call a green state. As you sinter it, you now are relying on the same things we talked about before: capillary action, reduction in surface energy. These are going to cause these particles to form necks and grow together, and that's going to mean shrinkage. So unfortunately, even though 3D printing, we always talk about it as a net shaping technique, if you're doing powderbed fusion, there will still be shrinkage here, and that's going to be something you have to design around.
That said, very few additive manufacturing approaches even use solid-state sintering because it's so slow relative to other approaches. It's much more effective to do this in a furnace after the fact than it is to try to do it right there with the laser.
Oh, yeah, absolutely. Yeah, take the whole part off and just sinter it afterwards.
The other thing is that you can get, if you're going to try to sinter it, now your laser gets to a really high temperature, and that means you might get some sintering of particles that aren't in the part. So from a powder perspective, it's nice because it's like, oh, the powder that wasn't, hit with the laser, we could recycle it. But if it's so hot that powder is now forming agglomerates, you can't recycle that. That's now a different powder size.
And that's going to make it worse if your material is a high conductivity material, so it becomes a much harder problem to solve.
Yeah, and there's a positive to this as well, right? If your powder starts bonding together, it also will help prevent curling and shrinkage because it forms a tougher hold on the part. But it's kind of a trade-off in terms of what's more economical here. The other thing is that the powder that's right next to the part that's getting hot will also start to melt and bond to the part. So you get what's called part growth. So you get like a film on the surface of the part of stuff that is kind of melted to it, but not really.
So that's one option. We have another option, and that's chemical-induced bonding. Tell us about this one.
This one involves thermally activated reactions between two types of powders or with the atmosphere. So, for example, silicon carbide in the presence of oxygen will form SiO2, and that will bind together to form a composite. Same sort of thing happens with zirconium boride. And this actually often results in parts with very high porosity that pretty much require infiltration or some sort of high temperature treatment after the fact in order to close that porosity up.
So a middle ground between these two then would be liquid phase sintering. Liquid phase sintering is pretty rad. You need to have a component that at the temperature where you're at has a small amount of liquid. You can't have a lot, right? You want a very minor component, maybe 3, 4, 5 volume percent of liquid. But what this is going to do is as it melts, it's going to fill into these gaps, right? It's going to, those regions that would be left with pores get easily filled. It greatly increases, because it's pulled in by capillary pressure, it's going to really increase your sintering time. It's going to go really fast to solidify. And there's lots of examples of this. If you're familiar with ceramic processing, you know that things like cobalt bonded tungsten carbide is a perfect example. The cobalt melts at a much lower temperature and binds the big chunks of tungsten carbide together.
Yeah, and there's a couple formations they'll use here. I'm just going to hit 3. The first are separate particles. So one of the particles in your powder bed is the binder, and one of them is the structural material. The binder material will melt when the laser hits, whereas the structural material won't. Yeah. So that will facilitate the binding together. The next are the idea of composite particles. So let's just say, right, you have your tungsten carbide and cobalt. You would cast this into something, so you have some sort of semi-homogeneous material, and then you would grind that into a powder. So now each powder particle contains a portion of it. And that one becomes pretty effective, but you still have issues where is the laser being wasted on these structural materials that aren't going to melt. So then coated particles become kind of the best option here. So every layer has a thin amount of binder, every structural powder material has a thin layer of the binder on it. And this means that it totally absorbs the laser power. It's not being wasted on the structural material. And because it's already where it kind of needs to be, it doesn't have to flow as much, so there's not any issues with it not filling in the right spots. And less binder ends up being required overall. The sintering's faster, it's a little more economical. This ends up being the better approach.
And then finally, if you don't want to just do a small amount of liquid, you could just completely liquefy it, right? You could just completely melt your component. In this case, your laser melting is going to be larger than the layer thickness, and so your previous layer also gets melted. So you can get good adhesion between these layers, obviously, and it's going to help lead to a very dense metal part. They make nylon components, for example, this way. But you do end up with part growth, and warping is pretty prevalent here. And so I don't know. I'm not sure if I see like one of these techniques really winning out over the others. There's trade-offs between them.
Yeah, and trying to mitigate some of those trade-offs comes into how they actually process it. So typically, for a given layer, they'll start by outlining the layer itself, and they'll typically go at a different speed there. And that increases the final properties and the surface finish at that point because they've gone a little bit slower or they've optimized it to make sure the surface looks as good as possible. And then they have a fill pattern for the part on the inside that's not exposed. And they can go a lot faster or be a little more loose with it because that part is on the inside. It's not going to be seen. And so when they're doing fill patterns, this is also a way to reduce some of the residual shrinkage. So typically, rather than just going, the entire cross section, just doing a hatchet pattern like they would with an extruder, they'll divide this into different strips and blocks. And so they'll typically try to randomize the orientation of how they're doing the fill pattern. That way you have different fill pattern orientations throughout the whole material. So they all kind of net cancel one another out instead of having, elongated large residual strains within the material. Particle size is another processing parameter. Smaller particles provide more surface area. They can absorb a lot more laser. They also contribute to higher powder density, which ends up being better for the final part.
Yeah.
They can also modify the laser power, the scan speed, the scan spacing. When they're actually optimizing this, they almost have like phase diagrams of sorts where they make the part with these different parameters and then they test the final properties of it. And so they can kind of characterize which properties yield what kind of part and try to optimize and figure out what the final properties, what the processing parameters should be to get desired properties. Generally, higher laser power and high bed temperature create dense parts, but can cause part growth. If you have a high laser power and low bed temperature, you get lots of shrinkage issues. So these are some of the parameters they think about when they're deciding how they're going to make a part. If they aren't well optimized, you can also get balling, where the surface area reduction causes the metal to actually just form a ball instead of creating some sort of layer, which is undesirable. A recent development that we alluded to earlier that has enabled a lot of these new engineering grade materials to be made is electron beam melting. So rather than using a laser, using photons to melt this, they're actually just using electrons like we would in a scanning electron microscope. And these are great because they're it requires less energy, about 10 to 20% of that of a laser. They can be controlled by magnets rather than mirrors.
Yeah, the same way that your electron microscope can shine it in certain spots, you can do the same essentially thing here.
Yeah, and so that's a lot faster, right? You don't have to have some sort of motor that's adjusting the position of a mirror. You can just instantly switch it with electricity and magnets, sparkling emojis around those.
Yeah. And I was reading about this, and you can do a lot more. In fact, this whole kind of field has been now started to be called direct energy deposition. So you can do it with electron beams, but you can also do it with wire arc. And this starts to look a lot like regular welding. Like you're producing material either in powder or rod form, the wire form. And this has been used oftentimes, it says here, it's helpful for filling cracks and retrofitting manufactured parts with the application of the powder bed method when it's limited there. So essentially, this is great for touching up. If you had powder bed problems with cracks, you can fill it in with this in directed spots. And as I'm reading about it, this sounds a lot basically like arc welding, like what you're really doing here.
Starts to get there. The problem is that the metal powder has to be conductive, right? If it's kind of like with an SEM.
For the conductive one, yeah.
Right. If it's non-conductive, charge builds up, which will then cause the powder to actually just start flying everywhere and create a cloud, or it'll repel the electrons, so it becomes a problem. So when they actually build the part, they have to build support structures, not for the metal itself necessarily, but to have like conduction channels to the substrate, which is kind of interesting.
Pretty wild.
The other thing is because it's using magnets, it can be moved instantaneously. Rather than using sort of conductive heating or some sort of radiative heating to keep the powder temperature, where you want it, they actually just move the beam rapidly over the entire powder surface to make sure it reaches an optimal temperature. And then where they need to actually sinter it, they wait a little longer there, which I think is kind of a funny approach. With these materials, you get lower residual stresses as well as higher bed temperatures. And the microstructures are often a lot finer. These will look more like cast part microstructures because the temperature is hotter and because the beam resolution is so much smaller than it would be for a laser as well. So rather than getting those lines that you see, which they can be mitigated with optimization, you really actually get a much finer microstructure within the materials.
All right, so what's the takeaway? All these different techniques out there. What's the takeaway is I think that the right technique depends on what you're trying to get out of it, right? If resolution is really important, if strength is really important, if getting a fully dense part is really important, all of these are going to play into which technique is the one that you're going to use, as well as speed and cost, right? Because these things certainly vary in cost. A binder jet printer, we just bought one for our department. It was not cheap. Whereas, fused deposition, that's like a couple $100 nowadays. So we hope this has been a useful overview. There's way too much to cover in a single episode when it comes to 3D printing, so we didn't even hardly touch applications in this one. We're going to do a follow-up episode where we dive into some of these applications and talk about the cool things that they're doing as material scientists with these techniques, but we wanted to lay the groundwork with how these work in this first episode. Today's episode is sponsored by our old friends, MatMatch.com. You know them, you know that we love them. They are a great resource for all things materials, and it's not surprising that they have some great resources for 3D printing. They have an article published just a year and a half ago called Everything You Need to Know About 3D Printing, the Ultimate Guide, where they go through a ton of the things that we talked about today, but with an emphasis on the materials that you're going to be using, what the limitations are for it, some of the techniques. We think it's a pretty awesome place to go. And obviously, if you're looking for materials, check out to see if what you're looking for is available on matmatch.com. It's no cost to use. It's pretty rad. I think that you'd like it a lot.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date in the latest happenings in the material science field and read some of their fantastic articles that they've published.
As we were preparing for this episode, I saw tons on 3D printing there. In fact, it's become really, every field has its own review article now on 3D printing. 3D printing for, steel alloys, 3D printing for ceramics. And so a bunch of those are available at Materials Today if you want to take a look at them.
Yeah, you can also head over to elsevier.com to find out about their journals, books, conferences, and other related programs that they host.
All right, as always, we are so grateful that you're here listening to us. If you can do me a huge favor right now, give us an iTunes review. For some reason, that is the coin of the realm. We know it's important, so help us out with there. And then check out some of the people that makes the show possible. Check out MatMatch, check out Materials Today. Swing on over to the people that make the music, like AlphaBot and Colobyte. They do really cool stuff, and they're always doing new cool things, so see what their music's about. If you have suggestions or tips for future episodes, we always love to hear it. You can find us on @materialism.podcast on Instagram, or shoot us an email, materialism.podcast@gmail.com. We'd love to hear what you have to say. And if you want to be on the show, consider sponsoring an episode. We'd also love to hear you, and we could talk about the right type of episode to make sure your product, gets to the right listeners.
The inventors of
See ya.
fire, electricity,
We'll see you next time.
magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.